So my presentation is entitled A Less Conventional Look at Risk. It could equally be called a slightly controversial look at risk, because I'm going to hopefully throw some good questions in to challenge you all. But obviously we all understand risk. In fact, I'd go as far as to say we're all experts in risk, aren't we? And I don't just mean the engineers amongst us and the engineers who are working offshore every day carrying out risk assessments. It goes further than that. We have soccer moms who are carrying out risk assessments for school barbecues. So we all have to deal with risk every day, and we all think we know what it's all about. What I'm suggesting is that although we all think we know about risk, maybe we don't, and I'm going to challenge some of the paradigms, some of the, if you like, conventional wisdom that exists around risk today. If I was to start by asking you, what is risk? I think a lot of you would come up with this. Risk is frequency times consequence. And it's a pretty good start. Clearly, the more frequently some unwanted event happens, the higher the risk. And the worse the event is, the higher the risk. But let's ask someone we all trust, Google. What does Google think risk is? This is the definition that Google gives. Interestingly, it immediately disagrees with what we were just talking about and starts to go into possibility, chance and probability. These are all likelihood terms, these are all frequency terms. So it immediately disagrees with us. So how would we talk about this in common language? These are a few statements or sentences that I might use. I might say the risk of me being late for a dinner appointment is high. It's definitely true, but it's actually the frequency I'm talking about, not the consequence, because the danger of me being late for a dinner appointment's not that significant. So I've used risk to mean likelihood. Similarly, I might say the risk from swimming in a river is greater than the risk from swimming in a pool. And again, we'd all agree it's true, but what we're talking about there is the consequence, because we haven't really mentioned the likelihood. I could also say the risk associated with driving is greater than the risk associated with flying. You'll have all heard this before. This comes down to exposure. If you never fly, clearly the risk associated with driving is greater. But if you never drive anywhere and fly everywhere, then the risk associated with flying would be higher. So it's purely, it's totally dependent on exposure. So we've now got a whole load of different meanings for the term risk. So my first point is we need to be precise. If we're talking to someone about risk, it's really, really important that we're talking about the same risk. We must make sure that we know what we're talking about and we're all talking about the same thing. Going back to the original premise that risk is frequency times consequence, is it really a product? Is it a multiplication link? Is it that simple? At the end of last year, I was watching BBC Question Time, and these two people were having a rather heated discussion about knife crime. So we're not talking about our industry anymore. Let's move risk totally out of there just to show that it's relevant everywhere. We're talking about knife crime. And they disagreed on a lot, but what they did agree on was that the amount of knife crime must be linked to the amount of the prevalence of knife carrying. If no one carries knives, you don't get any knife crime. If everybody carries knives, surely there'll be more knife crime. Fewer knives gives you less knife crime. That makes sense. They didn't disagree on that. If we put that onto a risk matrix, and this is a risk matrix here showing the likelihood of capture along the bottom, severity of punishment on the left, and if you move towards the top right, that's where you've got a really high likelihood of capture, in this case guaranteed, and life in prison, for example, as the severity of punishment. So the risk of actually carrying a knife, not the risk of being stabbed, but the risk of carrying a knife, is higher towards the right-hand side, the top right-hand side. The obvious implication here is that in order to stop people from carrying knives, you have to catch them more frequently and you have to have higher consequences. It seems logical, increasing the punishment and increasing the likelihood of being caught will reduce the number of people carrying knives. That would be the case if it was a product, frequency times consequence, but in the case of this, there are many, many studies that show knife carriers aren't worried about the consequence, they're only worried about being caught. So the level of punishment has very little effect on whether or not people carry knives. It all depends on whether they're going to get caught. So point 2 here, risk definitely doesn't always equal frequency times consequence. It might be a function of frequency and consequence, but it's not a simple multiplication, which we often assume that it is. A very quick segue into triangles, because it was in my title. We use triangles all over the place. We love them for warnings, they bring us attention to things. We use them as symbols to demonstrate hierarchies. Triangles are a really strong shape that we use all the time, particularly in risk management. One example, which you'll have seen, is the fire triangle, where you have oxygen, a spark and fuel, and together you have a fire. So there's something very primal about triangles that we use all the time. Someone didn't think triangles was enough in this case and made it a 3-dimensional pyramid, but it's still the same triangle. If you look on the internet for risk and triangles, you see hundreds of triangles. There's a whole pages and pages of triangles. This is just a few risk examples where risk and triangle came together. And it's just an observation. Triangles get everywhere, and we tend to believe triangles. There's something, as I say, very emotive about triangles, and everyone believes that if it's in a triangle, it's right. I once had a manager who, if he didn't have a triangle in a presentation, it wasn't a complete presentation. So the observation is that triangles get everywhere. Here's a triangle that most of you probably recognise, the ALARP triangle. My first observation here is that it's not actually a triangle, potentially. It's simply a line that goes from negligible risk to unacceptable risk or intolerable risk. There are actually, the way it's drawn, it looks like there are more things with intolerable risk than there are at the bottom with negligible risk, but it's actually the other way up. If, and excuse the pun, we take a leaf out of the urban forestry business, their ALARP triangle, apart from being tree-shaped, is narrower at the top than it is at the bottom, which makes more sense because there are a few items with an extreme risk and many, many items at the bottom with a negligible risk. But where does the ALARP triangle sit on our square? So we're now putting squares and triangles together. If you look where the ALARP triangle fits on this, I would suggest it's like this. The bottom left-hand side of the risk matrix is the broadly acceptable region. The intolerable point is top right, and there's this diagonal across the middle, which is the ALARP region. If we simplify that into a simple Boston square and look at the 4 quadrants, the bottom left quadrant are uncommon minor events. So these are things that don't happen very often and they don't matter much anyway. We then have up at the top left uncommon major events. Now these are your major accident hazards. They're very serious, but they don't happen very often. Down in the bottom right hand quadrant we have common minor events, which again happen a lot but don't matter much. So we're left with this top right, which we've said are intolerable, but we're calling them common major events. And what I'm suggesting is that these don't happen. We don't have common major events. It seems kind of weird that we have a risk matrix with this top right hand corner and we don't have anything in it, or very few things. So where are they? Why don't we have things? And I'm suggesting it's because of behaviours. Now, I've got an 11-month-old baby boy. He hasn't learnt behaviours yet, learnt good behaviours. So If you put him in front of a candle, he'll grab it. If you feed him food, he'll eat it. If you show him something shiny, he'll try and grab it. And if you put him on a table, he'll immediately walk to the edge and probably fall off. Now, he fell off his changing table just last week. He's fine, of course. But the point is that we learn these behaviours so early on in life that they just don't happen. We do really risky things. We drive down a road with cars coming towards us at 60 miles an hour, but we know not to drive on the wrong side of the road. It's just common sense. My 11-month-old, if he could drive, probably wouldn't realise that, and you'd end up with this major event being common. There are lots of things like that that we just take for granted. We don't drink boiling water. If we drank boiling water straight out of the kettle, then that would be a common major event. But some of these things are just so obvious and so built into our behaviours that they don't happen. So going back to this Boston Square, what I'm suggesting is that we actually have that and we've turned it into another triangle. So if we make that a bit bigger, so it's a 4x4 triangle. Don't know if any of you are recognising this yet, but we now have one of these things, which is called a risk triangle. And these are used a lot within our industry as well. You may recognise them more commonly like this. They're used to demonstrate essentially that for many, many near misses, there are fewer minor accidents, there are even fewer major accidents, and then there might be just 1 or 2 fatalities. So there's this hierarchy of incidents. This is a whole set of stuff that I got off the internet. Some of them about financial, some of them are about actual physical injury. But these all hark back, and they're used incessantly within our industry, but they all hark back to this guy, a guy called Heinrich, who in 1931 wrote a paper which suggested that, well, exactly what we just said. But what a lot of people don't realise in the business is that this pyramid that he had, he made it very clear it was a unit group of similar accidents. And in fact, they weren't just similar accidents, they were identical. They all had the same cause. And if you read into his paper, they were actually the same person. So this is the same person doing the same thing 330 times. And he had 300 no injury accidents, 29 minor injuries and 1 major injury, doing the same thing time and time again, the same guy. We have forgotten in this industry what that actually says. And the reality is that different accident types have different profiles of pyramid. So this 129-300 ratio is specific to this paper, and different accident types have different pyramids. So why don't we have a pyramid that's the wrong way up? Why is it that they're always pointy at the top? And the reason is behaviours. A pyramid like this would be more likely to occur if we didn't have that common sense aspect, because you'd have many, many common major incidents. And this might be a sport that gives you that kind of pyramid. This is actually a real thing, by the way. They do it in the Bahamas. They drag a shark on shore and then start wrestling with it. Not the brightest thing, I would suggest. Fortunately, because we're not an industry full of shark wrestlers, all our pyramids tend to have a point at the top. But as I say, there are different pyramids for different accident types. So what this slide shows is, on the right, a pyramid with all our near misses, if you like, all our minor accidents, majors, right up to fatalities. And it's made up, it's a composite of 4 other pyramids. Now, I might suggest that this one here is kitchen incidents, say avocado hand. You've probably all heard of avocado hand. You cut an avocado in half, you stick a knife in it, twist, and you take the stone out. Now, it's quite a big thing. A lot of people end up in accident and emergency with cut and lacerated hands, but they're never going to kill themselves and they're unlikely to lose an arm. So the light blue, the green and the yellow is as much as you get with avocado hand. Here, you might have major accident hazards or process incidents where you might have fires, explosions, and this is part of the summation that makes up your totals, but you might have some red incidents here. What I'm suggesting is that it doesn't matter if you ban avocados from the office, you're unlikely ever to start affecting the major accident fatalities. So the point here, point 3, is some near misses matter more than others, and it's really important to be aware of that. So we've had 3 points. Let's summarise. It's really important to understand risk. Make sure that the risk that you're talking about is the same as the person that you're speaking to. Behaviours matter. I'm not saying at all that behaviours don't matter. It's behaviours that stop us going into the top right-hand side of the risk matrix. It's behaviours that prevent common major accidents. I don't really want to use the word common sense, but good behaviour is what does that. And it's really important that we target the risks that count. This is the avocado argument. Doesn't matter if you ban avocados, doesn't matter if you insist that people reverse park, you're not going to affect the major accidents. You need to actually be looking at the thing that you want to target before you make a difference. So these 3 points, and just to keep consistency with the triangles, thank you very much. It's a triangle, hopefully you'll remember it.